This is chapter 4, part 3 from slide 21. We're going to use differential equations to study armor models, and this is going to be an exercise in using the algebra of the backshift operator and thinking about its relationship to differential equations. It's also going to introduce some ideas about the relationship between deterministic models and mechanistic models and time series models. So we're going to define the deterministic skeleton, but first, as some background, let's think about non-random physical processes. So time series, right, is all about randomness, but non-random physical processes evolving through time have been modeled using differential equations ever since the groundbreaking work by Newton a long time ago that set classical mechanics on its footing. When we do time series analysis, we normally have to attend to a considerable amount of randomness called unpredictability, or sometimes called stochasticity, present in the data and systems we want to study. But sometimes it's helpful to study a related deterministic system. And the deterministic skeleton is what we call a non-random process obtained by removing randomness from a stochastic model. Remember, our time series model itself will have to have a stochastic element to explain unpredictability in the data. For a discrete time model, we can define a continuous time deterministic skeleton by replacing the discrete time difference equation with a differential equation. And that's convenient because it gets us back into the framework developed by Newton. And then rather than deriving a deterministic skeleton from a stochastic time series model, you can also go the other way around, and you can take a deterministic model and then you can think about how to add stochasticity to get a model that will explain non-deterministic phenomena where you think your deterministic understanding gives you some good insight into the equations, but just doesn't give you enough stochasticity to explain data. Here's the example we're going to consider. We're going to study the AR2 model a bit. We're going to see, unlike an AR1 model, which really can only model kind of geometric decay, an AR2 model can model oscillatory behavior. And in physics, a basic model for processes that oscillate, such as springs, pendulums, vibrating machine parts, and so on, is simple harmonic motion. If you've taken some physics and you still remember it, then this will probably be a well-known equation to you. The differential equation for simple harmonic motion is the second derivative with respect to time of x of t is minus omega squared x of t. We'll call that M10. It's a second order linear differential equation with constant coefficients. So if you've taken a course in differential equations, then you'll maybe recognize that such equations have a closed form solution. You may even know how to solve it already. You may know that the solution is sinusoidal, it's sines and cosines. Okay, so finding the solution to a linear differential equation is very similar to solving difference equations, which is useful elsewhere in time series analysis. So maybe some of you have also seen how to solve difference equations. Often people study solving differential equations more than difference equations. Either way, this gives us a chance to review complex numbers. So let's see how it's done. Complex numbers will come up a fair amount in this course. It's one of these things that's sort of not critical to data analysis, but it's critical to some of the ideas underlying data analysis. So if you want to know what's going on under the hood, then the more you know about the kinds of things we're going to study with complex representations of oscillating systems, we'll be in a better position to do that. Okay, so we want to solve this second order differential equation for simple harmonic motion. And the trick is to look for solutions of the form x of t is e to the lambda t. And what's going on here, we have x of t is e to the lambda t. So dx dt is lambda e to the lambda t, and d2x by dt squared is lambda squared e to the lambda t. And so in M10, this gives lambda squared e to the lambda t is minus omega squared x, and we're looking for solutions of the form x is e to the lambda t. So we get the equation 25 that I just wrote there. And then the e to the lambda t cancels. E to the lambda t is positive, so we're not dividing through by 0. And so we get lambda squared is minus omega squared, which gives lambda is plus or minus omega I, where I is the square root of -1. Looks like we have some complex numbers to deal with. Now, this gives us two solutions. X of t is e to the I omega t, and x of t is e to the minus I omega t. But this equation is linear, and that means that if I have two specific solutions, any solution of the form, if the specific solutions are y1 and y2, then ay1 plus by2 is going to also be a solution. Now, it's a second order differential equation, so we expect to have two unknowns. That's like the two constants of integration. You integrate one, you have one constant of integration. You integrate twice, you have two constants of integration. And so if we have a general solution with two unknowns, then we're pretty sure it's the full general solution. There's not going to be any more. And so we can write the general solution as x of t is a e to the I omega t plus b e to the minus I omega t. Now, a wrinkle is that a and b could themselves be complex numbers. So what does it mean to be a general solution? This means that we know our solution is this for some a and b, but generally we'd need, say, initial conditions or some limit conditions, two extra conditions basically to pin down a and b. Now, it's not immediately obvious what that equation has to do with sinusoids. And to get the connection between e to the I omega t and sines and cosines, we need to recall the identities. Sine omega t is half e to the I omega t minus e to the minus I omega t, and cosine omega t is half e to the I omega t plus e to the minus I omega t. And okay, so that means we're going to start expecting that sines and cosines are going to figure. Now, I mentioned that a and b could be complex, but typically for real systems, we want x of t to be real. And so we get a couple of constraints. Well, we really get one constraint, that the complex part should be 0. So you can go ahead and do some algebra and work out the real and complex parts of 27. And if you do that algebra, you find that a and b have to have the form a is some constant e to the I phi, and b is minus the constant e to the minus I phi. And I'm going to call the constant big A over 2, and phi is some other real number. The algebra to show this is not critical for the course. It's a good exercise if you enjoy it. That basically means, depending how comfortable you feel with complex numbers, either when they show up, you just kind of hold on tight and get through it, and that's okay. It's not you don't really need big skills for manipulating complex numbers in this course, but if you do happen to have them, then practice them, and it won't do you any harm. The factor of a half is arbitrary, but it lets us write the solution as it is here in equation 29. X of t is a over 2 e to the I omega t plus phi minus e to the minus I omega t plus phi. And then from equation 28, you see that this is of the form x of t is a sine omega t plus phi, and that explains why the factor of a half was convenient. Otherwise, we'd get a factor of 2 in equation 30. And equation 30 is a nice form to have the solution in, because we can interpret a, omega, and phi in terms of properties of oscillations. So if you have a function of the form x of t is a sine omega t plus phi, then these, right, as I just mentioned, these parameters have names. Omega is called the frequency, phi is called the phase. Now, the exact values of these things depends on units. We usually measure angle in radians, in which case the units of omega are radians per unit time, so that omega t is radians. The units of phi are just radians. Sometimes when we think of oscillations, rather than thinking of the frequency, sometimes it's more convenient to think of the period. The period is the time for one complete cycle, which is 2 pi over omega. Because if t goes from 0 to 1, well, if t goes from 0 to 2 pi over omega, then omega t goes from 0 to 2 pi. A is called the amplitude, so that's the maximum distance from 0. And as we saw in the solution, A and phi are the unspecified constants in that differential equation, whereas the frequency is determined by the omega in the differential equation. Well, when you come to do data analysis and you look at practical problems, the units of the problem aren't always the same as the units that are most convenient for doing the math, so you have to be able to move between units. It's often convenient to rescale to cycles per unit time, in which case we put an extra factor of 2 pi in there, and then we have to rescale the frequency and the phase to be in frequency per unit time. There we go. So we have omega prime is omega over 2 pi, phi prime is phi over 2 pi. I guess that's rather not frequency per unit time, that's radial frequency. Okay. So now we've looked at that differential equation. We want to look at the relationship between that and a difference equation. So if we replace the second order differential operator by a second order difference operator, we get the delta squared is 1 minus b squared. And so if we just take that simple harmonic motion equation and replace it by the second order difference equation, we put delta squared yn is minus omega squared yn. And expecting that a difference operator is like a discrete version of a differential operator, if we sort of expect this, the solutions to this are going to be a little bit like the simple harmonic motion that we saw. We want a stochastic model, so we're going to add white noise and we're going to expand out delta squared to make it look like an AR2 model, and then we get M11 when we do that. It is an AR2 model. Because of its relationship to oscillations, we might think it's appropriate for describing systems that have some semi-regular oscillatory type behavior, but also have erratic fluctuations. These are sometimes called quasi-periodic behavior. And such behavior is evident in business cycles, wild animal populations, anything that kind of cycles in a slightly unpredictable way. Okay, so now let's see what this model actually looks like. We're going to simulate from it. That's a good way to understand. Let's take omega as 0.1. So 2 pi over omega, which is the period, is about 60. We're going to take the white noise to be IID normal, and let's see what we get. So we set the AR coefficients from the equation that we had in M11, and we do arima.sim with those AR coefficients, and we also do ARMA ACF with those AR coefficients to get the theoretical autocovariance function, here autocorrelation function, in fact. And here we see them in these two figures. So we see x of t is kind of like what we reasoned it should be. There are peaks every 60 or so time points. So there's 1, 2, 3, 4, 5 peaks before time 300. But there's also some randomness. It's not perfectly regular like a spring or clockwork. In particular, you can see the ACF kind of tailing off like this. There are peaks roughly every 60 time units in the ACF. Now, when you have an ACF decaying like this, it's helpful to have this concept of phase locking. So quasi-periodic fluctuations are phase locked when the perturbations are not able to knock the oscillations away from being close to their initial phase. If there is stochasticity, you kind of know eventually the oscillations are going to have random phase. They have to if they have a long-term stationary solution. And so this, we might be interested on the timescale this happens. And in question 4.6, we're asked what's the timescale on which the simulated model shows phase lock behavior? What timescale does the phase of the fluctuations lose memory of its initial phase? Well, let's just go back to this figure. And let us kind of connect the peaks. I'm going to draw the kind of the envelope here of the ACF, and well, I want to measure the time scale on which it decays to 0. Of course, it takes infinite time to get there, so you need to pick a cutoff for how long it takes to get there. My cutoff is going to be a half. And here we see that the that's about, this is roughly 2 cycles, right? So this is about 120. And now I can go back and answer that question. Let's say from the autocorrelation function, we see that after about 2 cycles, which is t is approximately 120, the autocorrelation between periodic peaks has dropped to a half, and we could say, you know, decay is often measured by the half-life, right? When for radioactive decay, for example, the half-life of the autocorrelation is about 120 time units. There we go. And that is the end of chapter 4. Thank you.